particle size is obviously one of the important proxies or particle properties, I guess, that we get by directly most closely linked, I guess, to the beam attenuation and scattering material that you've been having class. Okay, so this is just a quick, very sort of practical intro to particle size distributions. And I'm going to give you some code that you can then take and adapt and change the language or whatever as you start to think about not only particle size distributions, but also fitting models, data, and it's useful. So I just wanted to quickly start with a kind of survey. This is like a pattern they follow. I don't know this, but so when we think about the ocean, what are some important like particle size dependent processes you might care about?
Element fluxes, but element fluxes, but fluxes.
Okay, so it's like element like sinking
Yeah.
particle. Okay, sinking. Oh, that's a bad color. Let's try. All of these are going to be bad colors. Orange, yeah. Yeah, that's much better. Okay. Sinking particles, okay. What about other things? Yeah, transport. Transport. Okay. Oh no. Maybe we don't care about particle size. Yeah.
I guess turbidity for light availability.
Okay, turbidity, particle size dependent. Are there biological processes that include some relation to particle size? Oyster food?
Oyster food.
Yeah, what oysters eat? Might be like not directly related, but like atmospheric deposition. Okay. Deodorant. Okay, so there's some very diverse topically, right, sort of things that intersect with particle size. So I'm sure you'll think of some other ones, or you already are other ones as well. So methods we can use to measure particle size directly, not by proxy, might include like filters, right? Sieves, maybe these sort of physical separation. We've already done a few of those in our labs. We might also use cameras or imaging sensors for larger particle sizes to actually look at their projected areas and then determine their size that way. Other ones you guys are aware of? Microscope, yeah, microscopes. Okay, so there are some ways that we can kind of validate our particle size measurements. And then if we want to try and do it maybe faster than some of these. What? Or drop back up using my my Apple iCloud account to project things back and forth between my devices. That was the first. Okay, and so then our optical proxies, we've already talked a little bit, we got in this part of lecture, Wayne's lecture yesterday, but did you talk about slopes of beam attenuation and the slopes of scattering spectra as potentially, okay. Oh, and I just lost all my annotations because of that too. That stinks. Okay, I'll fill this in later. But optical proxies, so our IOP spectral slopes for scattering and beam attenuation, dynamic light scattering, maybe another optical proxy for particle size that often gets used. Sometimes the spikiness in your bulk IOP signatures, like if you're using a profiling float or a glider or something, you'll keep a high frequency time variability of your signal back to something about particle size. So there's a few different ways that we're applying these optical tools that we're learning about now to get at particle size. So we're shortly going to start putting those things together. And in advance of doing that, I just want to give you some vocabulary. It's there. So size distributions in the ocean for particles, organisms, etc., have been kinds of interest for a long time. There was a pretty classic paper, Sheldon et al. In 1972, that sort of tried to take this broad global approach to cataloging what's the size distribution of everything from phytoplankton to whales, right? Like, and this is a biological approach. And just with their sort of rough, first order measurements compiled from a whole bunch of different global sampling stations, they found that to first order, there's roughly about the same amount of material in like spread out across logarithmically spaced size bins in the ocean. And so this is consistent with a power law function with an exponent of -4, right? So there's this sort of canonical particle size distribution function that think of that we think of. And so that number of particles as a function of diameter approximately equal to diameter raised to the -4th power is has these important ecological implications. So this is sort of saying that, for instance, growth rates need to be inversely related to particle size if this canonical value holds everywhere, or that the processes that are producing small particles and the processes that are destroying large particles kind of need to be in balance across a huge size spectrum for this to be true. So there's sort of interesting kind of theory, and like it goes into ecology, it goes into aggregation and disaggregation and resuspension and all of these things.
Sorry, the big growth rate, they will be very population,
Growth of the population. Yeah, so this is like here they're looking at time to double in hours, right? So that's sort of a population. Yeah. So when you're looking at particle size distribution observational data, there's some important things to think about. So if it's come out of an integer or come out of a sieve or something like that, right? Important things to think about first is what's the instrument sample volume? How many particles is it likely to capture in a single measurement? And particularly if you start thinking about those rarer, larger particles, how many is it reasonable? If you're trying to figure out the biomass distribution of sharks in the ocean, and you're taking 4-liter Niskin bottle samples, it's unlikely that you will ever capture a shark in your Niskin bottle. Maybe for some other reasons besides their distribution as well, but they're too big and too rare, and so really you need to come up with another weight sample at that size range. However, if you're trying to look at the size distribution or the numbers of phytoplankton sized particles, well, maybe your Niskin bottle is actually a pretty good tool for good statistical representation there. But that's actually, that's pretty important when you're thinking about larger things. Thinking about sinking particles or biological carbon flux, right? The bigger and bigger and bigger you go, the more important it is. The other thing to think about in terms of observational data for particle size is what's that method's lower detection limit? What's the smallest thing that it can see? And when you get towards that low end, do you expect for your instrument to see a roll off, right? Like, will you just stop detecting as many things when you get to the very smallest size? Or will you see a spike, right? When you all of a sudden start counting your noise as many particles and it goes up. Either way, you might expect to see some artifacts at the ends of your particle size distribution spectra, depending on your method. So like when we start using a list to estimate particle size distribution, what do we expect the list to do? To get very, very small or very, very large. The figures I'm showing you here are from a pretty classic paper by George Jackson in 1997, and this was a really it's a good read if you're interested in PSDs or interested in like getting multiple instruments that are very different to all agree with one another. Really nice paper, but they basically took all the different instruments that they could get their hands on at the time for measuring marine particle size distributions, put them in the water at the same time, comparing them. So these are all log plots of the number spectrum, so number of particles in per volume, or I guess linked to the -4, right? So that would be per volume per width of particle size bin on the x-axis and the diameter on the y-axis. So you see this sort of, they're not exactly linear, right? So there's definitely, they don't completely follow that power of the 10 to the minus, or that diameter to the minus 4 power law function, but kind of. Okay, also this particle size distribution slope. So the, again, canonical assumption would be that value would be 4, right? So number of particles, model it, number of particles equals the number at a reference diameter. Not. Times the ratio of the diameter to the reference diameter raised to the power -4. That's what might actually fit to our target size distribution data. Yeah, this is here's some data from the study by Hale, who's going to be here, I think, in the 4th week of the class, right? And this was, I think, from that maybe. But this was a nice combination of a whole bunch of different measurements of PSEs and samples from Niskin bottles, sediment traps measured by a number of different methods, right? Using the list, using the imaging flow cytobot, and in sort of different pools of particles in the water column and sediment traps. And you can see that even at a single site, this was the leucotropic white time series site, there's power law exponents on these size distributions. None of them are 4, right? They're all actually lower than that. And you can definitely see that there's a difference between particles measured in suspension and particles measured in sediment traps, which we might expect, right? Particles sinking, you're going to have a flatter size distribution that is more larger particles relative to smaller ones compared to ones that are not sinking. So there's definitely interesting trends here. This is, one way I think of modeling the particle size distribution. You can fit any function you want to any data. So maybe there's a better way to do it than just the power law. So what we're going to do next is just work through a simple example. I'm going to, there's actually a folder that I put on the share drive, or not the share drive, that's like some code and a data file supporting this lecture on PSP. There's a data file from Imaging Flow Cytobot, and then there's 2 MATLAB scripts that are standalone functions that you can run and play with. And then there's a live script that is actually going to run the same functions, but in small chunks, so that you can walk through it with me. I'm sorry, it's in MATLAB. That's but you're more than welcome to take any of that code and remix it, plug it into ChatGPT and turn it into whatever you prefer to code in. And it's just kind of, if you haven't thought about particle size, maybe a useful place to start, and to think about binning data. And understanding what bin data look like, how do you choose your limits for your size distribution? How do you know that you're kind of getting good statistics in each one? So that's what we're going to go through next. Well, if you want to run with that, like grab it and get it going on your computers. Just quickly, if you have never looked at data from an Imaging Flow Cytobot or phytoplankton data, this is a instrument that's basically taking a stream of seawater and imaging individual phytoplankton as they pass through the sampling chamber. And so this is just some thumbnails, some examples of data you might get. So each particle, we've got its area or size estimated from an algorithm that looks at each individual. So we've got a bunch of counts and diameters or equivalent regular diameters really associated with it. And from those, just a list of particles and their sizes, that's what we're going to start. We're already assuming you've somehow figured out a way to count the number of particles and their sizes in a sample somehow. So I'm going to quit sharing this and switch over to my computer. There's no MATLAB on iPad as far as I can tell. Okay. Question? No questions. All right. Are there questions while I'm
switching over right now. Okay, and we only have like 10 minutes before lunch, so I'm gonna move quickly, but I'm happy to stop and go back through anybody who has questions. So, so if you open up a live script in MATLAB, that's the MLX file. It's just set up in blocks. And you can run each one on a Mac. It's Command Shift Enter. I'm not actually sure what it is on a PC to run each block, but if you're not a MATLAB user and trying to figure this out on the fly, probably a neighbor can tell you. So the first block is just going to read the data into the workspace. And this particular sample has a volume associated with it in milliliters, and I'm just going to convert it to liters. So we're going to get data that are going to be like number of particles per liter. And it has read that in. And I'm just going to, this is again like data wrangling here. I'm just going to pull in the size of each of the particles in the data set, its area, and a volume estimate based on an algorithm citation here. And then the number of particles. So there's 3,393 particles in my data set. And the first thing I'm going to do is just always make a plot and look at them. I'm just going to make a histogram, but I'm using the number of bins equal to the number of particles so that it's just going to make 1 bar per bin just so I can see the data. And that's going to generate a figure. It should have generated a figure. Why did you not generate a figure? Ah, you're just slow. Okay, so so we see that we've got, so this is our just raw data diameter of particles on the x-axis and number counted on the y-axis. These are just linear. So we can see that there seems to be, right, a much larger number of particles at smaller sizes than larger sizes, only it seems to decrease as we get into very small sizes here. And so we will think about that a bit more here in a second. So I'm going to make an initial pass to bin these data and arbitrarily choose 10 bins. It may be that we decide that's maybe not the right number of bins later, but for now, I'll just start with 10. And, you know, there's 3,000 particles, so 10 bins should, you know, at first glance, give you pretty good numbers in each one. And I'm going to set that up in log space because we expect particle size distributions, right, to sort of move more at small sizes, less at larger sizes. So I'll go from 8 to 200 microns, take the log of both of those, and then find the edges of those bins in log space and the centers of those bins in log space, and then go back to linear coordinate or linear space. So I'm going to run this, and then I'm going to plot, just make a graphical depiction of what those bins look like. So here, the centers of the bins are the dashed lines, and the edges of the bins are the solid lines. Right, so we're going from 8 microns to 200 microns. So you can see we've got these log space bins, and these bins are not of equal width, right? We have wider bins for the larger size particles and narrower ones for the smaller size particles. So we'll want to keep that in mind when we normalize our data later on. So now I'm just going to do a histogram function to bin all those particle sizes into my bins. And so going up this from the smallest particles to the larger ones, we see we go from a few hundred to over 1,000 and then tail off again. And the largest size bin has only 3. So I'll make a plot of those data, and I'm going to do just 2 versions. One that is linear, so number of particles as a function of diameter and diameter. So here's the linear version, and then the log version of the same thing. So we can see already looking at these data that there's this weird kind of drop in particle counts in the smallest size bins that I've kind of arbitrarily chosen, right? And so this is probably a case of, as we get down to, you know, sub 20, 25 microns, we're not resolving those particles as well anymore in this instrument. So maybe not detecting them as well. So maybe this is a situation where we'd like to adjust the size bin edges. So I'm going to make a new set of bins. This time I'll set the minimum to 25 microns instead of 8. And rebin. Okay. With new bin edges, new bin centers, and particles are now binned into those new bins. And I'll replot. Yes.
That, do they add up to the same, so it's just. You have it now.
So we've cut off the ones that are smaller now. Yeah. So we're just saying, okay, anything smaller than this, we don't trust that our instrument can properly resolve it. It might be noise, it might be, we're not sure. So just, yeah. So yeah, so we've now got the largest number of particles is only 446 in that small bin that starts at 25 microns.
So you cut out anything. That
Yeah. And maybe that's not the right choice, right? That this is a sort of arbitrary sample of particles that I don't actually know very much about. So maybe you think about like, okay, is there a real reason we would expect to see a loss of counts in the smaller bins? Is there something about those particles that we expect to behave that way? But here I'm saying, it might be instrumental. I'm just going to ignore it for now. So I've now replotted those data with the new size bins, and now they're kind of behaving a little bit more like we might expect if we thought that particles should follow a power law distribution-ish in the ocean. So here's our linear version of the plot and our log version of the plot. So you noticed our particle counts in those largest size bins are pretty low, right? 6, 3, and 2 in the bins that are centered at 119, 146, and 180 microns. So is that, how do we want to interpret it? You know, our particle size concentration or particle concentrations in that very high size range when there's only 2 or 3 in a bin. So one way to try and account for that is to estimate the uncertainty in those bins. And one way that often gets used in these sort of particle data sets is to assume Poisson counting statistics. So Poisson distribution is like, you know, what's the probability of something, an event occurring if we know the mean rate at which it occurs, and if each occurrence is random, right? Uncoupled to the next or the previous. If that is the case, and you know, if you're sampling a random bit of ocean water, it's probably okay to assume, all right, there's some mean concentration of every size in there, and whether or not we happen to capture some amount of that particle size in our blob of water, right, is unrelated. Like if we get another sample unrelated to the first one, we get another sample unrelated to the second one. So, so we can make that assumption. And then if we are following a Poisson distribution, then we would expect the mean to be the mean rate and the uncertainty to be the square root, right? So processes that follow Poisson distributions will have a mean and standard deviation of the true mean plus or minus the square root of that. So for our counting uncertainty, we're going to assume that the uncertainty, like from each across independent realizations of the same sample, should be the square root of the count. So we'll compute that. That is, we've got this mean count in each size bin, and the square root of that count is the uncertainty in that size bin. And so now we can use that assumed Poisson counting error as our uncertainty. So I'm going to make another set of plots, this time with error bars. So again, linear version and log version. And as we see, as we get towards these very large size distributions, it's pretty clear in the log side of the plot that there's large error bars there. So if we really were interested in things happening out here, maybe we're trying to estimate a carbon flux, maybe we're trying to compare to some optical proxy that's measuring spikes or something, maybe we'd want to adjust those bins again and try and get better statistics in our large size bin. I don't want to break the stick.
Okay.
Okay. Okay, but this is sort of one way of getting at the uncertainty in particle counting type measurements. So finally, right now we're looking at just the number of particles as a function of size relative to size, but the bins aren't the same width, right? We saw this earlier. The large particle size bins are quite wide compared to the narrower ones. So if we actually want to fit a distribution to that, or importantly, if we want to compare the particle size distribution measured with this instrument to a different instrument that maybe has completely different sensitivity or sample size or something like that, we need to normalize to the bin width. And here we want to normalize to the volume sampled as well. So we're going to change our particle size distribution units from the number of particles to the number per liter sampled by the instrument. And then for each bin, we're going to normalize it to the width of the bin. So we take account of the fact that the smallest bins are much narrower than the widest bins. So now we have the number concentration in normalized fashion. And I will plot that. Okay, and so now we've got the log. This left-hand plot, or right-hand plot, is the log of the number concentration as a function of diameter normalized to diameter. So the notation here is ND/DD. You will see that in some particle size distribution literature. And sometimes you'll run across papers where they don't do this, or you have to really think carefully about it. Am I doing an application where I want sometimes this is called the differential size distribution. And this is what you want if you're trying to fit a function or compare a trend. If you're trying to determine what's the total volume concentration of stuff in my sample, then you want to integrate. And then you don't want the differential size distribution. You would need to multiply through by the bin widths. So it kind of depends on what you're planning on doing with the data, but this is the differential size distribution for this sample. So then if we wanted to fit a power law model and figure out what is the size distribution slope, or maybe if we wanted to fit a different model, and there'll be lots of, I guess actually you've already done some fitting of, like to get your CDOM spectral slopes a couple nights ago. There's been some function fitting. I don't remember if we talked a lot about like what's the best way to do it. Do you just log transform it and fit a line? Here, what we're doing is we're doing a least squares minimization of our data to a power law function. So it doesn't require us to log transform anything. So there's a separate script that this is going to call called PSD compute D naught. And basically I'm going to feed it an initial guess. So if our size distribution function we're going to fit is ND equals ND at the reference diameter times D over D ref raised to the spectral slope. We're going to do an initial guess of, well, we'll define what D ref is. And here I'm just going to arbitrarily say 100 microns. And then we feed it an initial ND ref and spectral slope. If your model is a decent fit for your data, it shouldn't matter what your starting parameter guesses are, right? If you find that messing around with that initial parameter guess causes the output to vary a lot, then that means you should be questioning whether your model is a good fit for your data, or if your data are too noisy and have a lot of uncertainty that needs to be treated a little bit before you try to fit a model to it. So what we're going to do is pass these initial parameters into a function that's basically going to minimize the power law spectral slope and adjust the parameters to optimize them. So here we get the number concentration at 100 microns, and power law spectral slope of 1.78. You can do interesting things like vary the data, like you can perturb the data and do a Monte Carlo approach to try and generate uncertainty estimates on these parameters as well. And I'll talk a little bit about that later in the course. So then finally, we can plot the data again with the model fit to them. There we go. So again, linear log, so we can see, okay, kind of a decent fit, but in this case, to me, it looks like there's actually some information in that size spectrum that's not well captured by the power law. Maybe there's a population of phytoplankton or something that are causing that deviation there, or maybe we want to fit a sum of Gaussians or something like that to better describe the components of the particle size distribution. But this is a good first pass. And if we were going to try and use a proxy like the beam attenuation spectral slope or something to get at the particle size distribution, we would probably be comparing it to a model like this. So yeah. So anyway, this is just a quick breeze through treating particle number data and figuring out how to bin them, how to visualize them, and how you might go about trying to estimate uncertainty and fit a model to them. So the code is there. If this is something you've never done before and you want just sort of some basic building blocks, that's the point. If you have done this before and you have your own way of doing it, you can just totally disregard, but feel free to play around with it. Questions? No, great. And it's lunchtime.